Sorry about that. It's an interruption by Chinese wife. Well, I thought it was amusing, so I'll leave it in. I won't edit it out. A bit of the human touch. Okay. All right. So getting back to left brain stuff. So you're given that for your group, every element, if squared, gives you the unit, and therefore it's abelian. And the statement of the theorem is as follows: that well, instead of calling it G, call it A, because we now know it's abelian. It's an abelian group. So here's the theorem that this group A. Maybe I'll try a new one. That this group is in fact isomorphic to the following direct product. In fact, it's a multiple direct product. Yeah. So Z of 2, Z of 2, Z of 2, dot dot dot, Z of 2. Yeah? That's the theorem, and we'll actually prove it, and then only discuss but not prove the next two. So 39 and 40. Okay, now this is n times. So you may ask, well, what's n? How do you know what n is? Well, to give you the answer, go back a bit within this lecture. N is the size of your minimal generating set, your MGS. Okay? So that's what n is. So, and later we'll take this formula, this form, and we'll generalize it into a very famous theorem. In fact, it's this one. So, and do theorem 39, but not prove it. Okay, so how to prove this? And n is the size of your minimal generating set. Okay. So how to prove this? Now remember this Z2. What is it? It's the set of residue classes. Okay, and its orders and it's actually a group, and the order of this group is 2. So the size of this multiple direct product, and we have n of these, will be, you know, order 2, order 2, order 2, will be 2 to the n, right? So the order of this is 2 to the n, and hence so is this one, right? Must be the same order if they're isomorphic. Okie dokie. So if we're going to prove this, you know, we're proving an isomorphism again. This lecture is about isomorphisms. So you know the usual 3 steps. Well, first you've got to find the mapping function, your f, and if group A is isomorphic to B, group B is isomorphic to A, so you can map either way, right? So what do you suggest here for the f? Which way will we map from to? So well, we had something pretty similar to this, you know, a while back, and let's call this just D, right? So just group D. So that's D, and so effectively we're trying to show that A is isomorphic to D. You know, D's just this, right? So so we're going to map A into D, or we're going to map D into A. We had this question before. So, well, Barnard, he maps D into A. Okay. And so what's the actual, you know, that's in terms of groups. So what's the actual element mapping? So what's the formula for f? F of what will give you what? Well, we've had, well, yeah, I'll just write it out. So now look, this is a multiple direct product, right? So the elements of this group will be of the form, look, will be of the following form. Integer, comma, comma, r to the n equals now we're told that the size of the minimum generating set is n. Alright, so that means with those n elements that belong to that minimal generating set, we can form any element, okay, that belongs to A. So the general form that an element of A has will be of this form. So it'll be A to the 1, R to the 1. And here's your mapping, right? Well, here's the connection in a sense, right? R2 dot 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 A n r to the n. Okay. Now this suggestion for f is critical because the rest of the proof depends on it. So it's important to make a wise choice for your mapping. As you like, one choice was which direction do we map D to A or A to D, and the choice of which element, the general form, which element gets mapped to which element, that kind of thing. And so just here is really, if you think about it, is really the heart of the proof, right? Because all the rest follows from this. So these initial assumptions are critical. Okay, I assume you appreciate that. And so what is this? This is an element of this multiple direct product. Right? Now, if you're used to that, just two, the direct product of two groups, then this element would be of just of this form, with a right bracket here and a comma. But this is like n times, so we'll have comma, 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 and that's an element of this multiple direct product group, right? So we're going to map that into that. All right. Okay, so we've been through this kind of thing several times. So what do we have to do? We have to show that it's well formed. Like if now these numbers here, these integers here, they are, remember, representatives of the residue class. So if I change these to S1, S2, Sn, and R and S are congruent numbers, will I get S1 here? So I need that to happen. Otherwise, my definition is not well formed. So talking about whether this f is well formed, I need to show that if I put S1, S2 to Sn, I get a result where I get S1, S2, Sn. So this this and this they match. Okay. So how to do that? So if this element, if R1, R2, Rn equals the same thing but with s's. Maybe my sweaty hand. Okay, so if that's true, then R1 and S1 are congruent, right? So we have to prove that f of these gives us this. Okay. So now if that's true, that implies that Ri, the general term, take the ith one, is congruent to Si. And what's the modulus? Well, it's 2, right? Because all these, the order of each element except the unit is 2, so this will be mod 2. Right? And now we use theorem 18, part 2. If you can remember, go back a bit. If this is true, if I is congruent to Si, modulus, the order of, well, in this case 2, the order of your elements. Now, if that's true, then by part 2 of theorem 18 on page 45 of your text, then the a to this power, a to the Ri, is equal to a to the Si. I'm going to go for a completely new one. These are all dying on me. Right. Okay, so a to the Ri is equal to a to the Si, and so you just plug these into here, and you get a to the A1 to the S1, A2 to the S2, and so forth. This is in general. So you just plug. You substitute this for this n times, and you'll get what you're looking for. So it's well formed, right? Right. Surjection. So we're mapping. What do we do? We're mapping D, mapping this into this. So every element of A is of this form, okay? And you can generate these from the minimal generating set, okay? So for any element in A, it will be of this form, okay?